And now we can continue our discussion of two-variable data. We'll do some nice problems. I did some of them myself, and I found them to be very nice. Perhaps this is a good problem to start with. So as usual, 65 seconds. Okay, this is not usual. I give 60 or 70. Now I'll get 65. Because I feel like it. Why not give you 65 seconds? Yeah. So maybe I give you a bit more time because I was writing something down. Let me start writing down some stuff. So here you have this plot. The general theme is you get a set of points which look scattered around and weird, but you can fit some function to the set of points, which kind of mimics what happens in these gaps. So you have certain points, but let's say you want to find out what would happen if you were approximately here or there, for example. So you would approximate this data point to this value, for example, and so on and so forth. It's useful if you want to make predictions about things. So that should be a nice introduction. What do we have here? It's an equation. Y is equal to 0.096x minus 0.488. Now, with word problems like this one, it's a good question to ask yourself what x and y are in this position. Maybe I'll ask you or you.
What's x?
So what does x represent in this problem?
The years.
Years. You mean the change in years?
Yeah.
Okay, and what does the y variable represent?
Minimum wage.
Minimum wage in dollars. Okay. So you give it a number of years since 1940, let's say 10 years have passed. Then you have minimum wage, which is roughly $1, less than $1, for example. Now, we would like to understand what this means in the context of this mathematical statement. I mean this one, so this representation of a function. So what happens with each one step x? First off, what is one step x? Well, yes. Well, not one step. Okay, maybe because we're taking steps in 10. What's 10 steps of x?
10.
10 what? 10 years.
Oh, yeah, I think.
So 10 years. And then you obtain some value for the minimum wage. Okay. Now, this is a linear equation. We know that the linear equation describes two things: the slope, number one, and the y-intercept, number two. The slope is always the change in y with respect to x. Right? This is what the slope is. We already know this. Okay. You could also describe it as the average. So maybe that's a hint towards where we're going. And then, how do we make progress with this? So perhaps it would be a good idea to see how we can interpret this statement. So again, y is the change in years, right? So y is years. So my apologies. Y is the minimum wage. So y is the change in minimum wage. And x is the number of years. So change in x is the change in years. Okay, so the change in one step of the minimum wage with respect to the years is 0.096. How do I say this more precisely? I would say that the change in the minimum wage with respect to each year, because the year is always the input, change in y, minimum wage, with respect to x, which is 1 year, for example, is 0.096. 0.096 can be written as 0.096 over 1. Now, above is the minimum wage, and below is the years. So I hope that makes sense. So the rate of change is 0.096 cents per year. In 10 years, this should be roughly $1, I think. So 0.96. This is a bad dollar sign. This is a better one. Okay. And then this first fact should help us find the answer, and this other fact should help us eliminate some solutions. So let's take a look at the ones with every 10 years. It says that every 10 years, the change is 0.096, which is unfounded. Change in 10 years is almost $1. I mean, you can also notice this. I mean, if you just look at the graph, roughly in 1 year, in 10 years, the change is almost $1. And it's also not half a dollar. This fact. And then we have two statements, one that says 0.49, which is not correct, unfortunately. because I'm not even sure where you get this figure 0.49. How do you obtain this? So it only leaves us the last statement, which is a reformulation of what we were saying in the first place, and that is for each year, each one step x, we get a change of 0.096 in y. So 0.096 of the wage. The y is the wage. So it's basically just a way of reformulating mathematical statement into words. So that's good. What do you think of this? Have you done it in a different method, perhaps? Maybe you guessed it or something. Maybe you used decimals. Okay. If you have questions, we can talk about it. But if it is clear, then this should be a nice problem for you to attempt. 60 seconds. Talk about it now. Talk about it now. So, I think having points, and I use them such that the average is 3.1. So I put some 11 points. So I put 5 points really down below. 5 points up. The median is the point. The sixth one. This is always the median. Same thing here. This is always the median. 1, 2, 3, 4, 5, 6. So here, I choose the points such that their average is 3.41. This kind of cancels out with that one. And same thing here. So these ones kind of weigh out the other ones, so we'll be in the middle. Oops. These ones don't weigh out. Maybe I should do it like this. And do like this to hold the average up, because this is downwards. So if I just put 2 points really high up, then the median is downstairs. But then notice that this average is less than that average. The median is the same. It's not the same. The median is less. So you also have this freedom.
Yeah, it's kind of
I agree with you. If I choose nothing, it's very big.
Yeah, I agree with this.
Yeah, just choose.
By the way, the last question, what was it? 0.96. What year?
96.
0.0. Every year or every 10 years did you?
No, every year was the answer. Because with each step, X.
Yeah, that's one.
Yeah, so it's the one that's. This is the most precise way to say it. Okay. So we've done linear functions. We know that any linear function is defined by two things. Number one, the slope. Number two, the y-intercept. So if I look at this function and see roughly where it intercepts the y-axis, which is this one, then it's clear to me that the answer is definitely not 300. It's definitely not 82. Sorry, 84. Because the y-intercepts will never be like this. Is this clear for everyone? Yeah. Okay. Then I now need to focus on the slope because the y-intercepts are the same. So there is a huge discrepancy between these two. Here you're saying that with each step t, where this is the t-axis, you get a 0.03 change in the sales D, which we can inspect. So let's take a look at what happens, for example, within 2 steps. So I take 2 steps t. So this is 2t. You can zoom in on this. Now what happens? I'm almost at 500, and now I'm at 550-ish. I'm not sure if you can see it. If you can't, let me know. And the screen should be big enough for you to see it. No doubt about that. So it's roughly, 550-ish. And it roughly started at 500, then probably the change here is, 50-ish. There are 2 steps. There are 2 steps. Yes. Then probably this is not the answer. Now, this does not have to be accurate, guys. This tells me actually that the slope is 25, and it's not. It's not going to be 25, but it's definitely not going to be 0.03, right? I hope I'm not hand waving this. If it's not clear, please let me know. What do you think? So you just look at the graph, and you take a look at the change in D dollars with respect to the change in temperature. So if you take 2 steps in the temperature, this equation says that your sales should change by only 0.06, which does not make sense really. 0.08. So this is more realistic and will be our answer for the exercise. What do you think of this? That's good, right? So the other 2 can bait you because they have 33T. Okay, this looks a bit realistic. The graph looks awful. You cannot really extract any data from it, but it might trick you at the start. But then there's no way this is going to be the y-intercept. So you immediately cross out these 2 values. Are there answers on Teams? On Moodle? Okay. Let me double check this just to make sure we don't make a mistake. Yes, we did make a mistake. And that is okay. This is good. I think we can actually learn from this. So here, this is not the y-intercept. That's where we made a mistake. This is not the y-intercept. Y-intercept is when t is equal to 0, but here t is equal to 10. So I'm actually happy that we fell into this trap. Okay, not too happy because we lose a little bit of time. It's a good lesson. Thank you for pointing this out. Yes, so this is not quite the y-axis, so probably we won't really be using this. But then we need to find another strategy. In this case, approximating the slope won't really take us too far.
Exercise told temperature is T, so I only do that value of T. It's near the.
Yes.
And I put it in the formulas.
So which 2 values did you take?
I2, 16.
16.
And I put it in the formulas.
It's almost 600, right?
Yeah.
So almost 600, okay. Ah, okay. Okay, so you took this point and you're like, okay, let me see which one will give me 600. Okay, that's not a bad way to go. Let's see. Ten times it was 16, right? We should get something close to 600. This is not the case. We plug in six. Yeah. So you guys did it differently and nobody alerted me. You're telling me go to
Well, we just
like just tell me something. You know? Like I can make mistakes. It's fine. No, yes, you should say that. You should state that. You should have the courage to do so. So that's good. Okay, so this won't work. This definitely won't work if you plug in 16. But if you try 33 times 16 plus 300, this also doesn't work. It's deep. Then probably 33 times 16 plus 84 is a little bit above 612 and it worked. But I also want to explore one more method you could tackle with. So this is a good use of the fact that 16 is almost 600, but you could also try to find another point. Let's say it's this one. Yes, so 22 and 800-ish. Just forgive me today. Graph is not really helping. So I compute the slope from here. 16. It's y2 minus y1 divided by x2 minus x1, or the change in y minus the change in x. 22 minus 16. Okay, that's roughly 33. Then probably that would help me pick two answers out. But then I think the only way you would conclude this is by actually plugging in numbers.
Yeah.
Yes. Then at least for the sake of time, it seems more sensible to proceed by plugging in values, maybe on decimals.
Yeah.
If you wish. You can also use a normal calculator. Okay, that's good. And there's also another problem that I really liked and I wanted to do, which is this one. Hopefully I don't get this one incorrectly this time. I'll make sure to not do that. You could try to plug this point in resonance, roughly, 790. 2 should give you 790-ish, for example.
And look this one.
So take a look and see which one should be. But if you know what you're doing, you can actually do it in much less time. So first off, we want a function that will kind of approximate this behavior. I'm not going to solve it, I'm just giving hints. If I had a line that goes through these points, it will probably look something like this. It's frowning. It's not an increasing function, it's decreasing.
Decreasing.
Right? Because it's going like this.
Mm.
And what else can we say?
Looks like a quadratic form.
Yes, I mean all of the questions are the polynomials are quadratic. Is it D? B. Is it B? I don't know, is it? Let me know. How did you get, how did you reason that B should be the answer?
If it's decreasing
Okay.
color, then it should be the highest degree
No, it isn't.
variable is gonna be negative.
Yeah, so this is a good fact to start with. So if you have a degree 2 polynomial and it's sad, then this a, which is the coefficient of x squared, is probably less than 0. It's probably negative. And if the opposite is true, then you have a smiley face. You have someone who's happy.
Say D.
It's I don't know. I don't know the answer. I'm not the answer key. I just made a mistake. The previous question, so I don't know. We need to figure this out together. But yes, this is the first fact. So if you notice the frowning face, then probably the first term is negative. Then A should not be the answer, and C should not be the answer. But how do you conclude that D should be the answer?
There's two ways. Either you can plug in. No, plug in the value.
There's a nice value which you can plug in.
No, I plugged in 4 or 10.
There's a nicer value. There's a very nice value which you can plug in. A very, very nice value.
Yeah.
0. So the y-intercept.
Yeah.
It's just like the linear function. It's this polynomial. When you plug in x is equal to 0, you get the y-intercept. Now the difference here is actually with the constant value, if you notice. So if I plug in 0, let's say I continue on with this graph. It is very unlikely that it goes on like this and then cuts at minus 745. That would be very bad, you know? And it's not going to happen. So what's actually going to happen is it will cut at 745.
It's positive.
Yes. So from here, so minus 745 is very, it's very down below. So just to give you a perspective, this is 120 steps. So you have to take 120 again. And then again, if you don't see this, yeah? So 360, and then minus 480 again. And then, okay, this is not a straight line, but just bear with me. 600, and then 720. Now you're at 0. So now you're finally at 0. Now you just copy this and you just say, I'm gonna do it, you know, again. I do it again. Forget about the line in the middle. So it's roughly here, you know, the y-intercept. If you pick the one to be negative, so you just have to do like this, you know. Do like, have to do like this. Yeah, and then okay, and then you know. Which is very unlikely. So I'll just erase this very bad illustration and just conclude with the fact that it's 745. And you can also do this by plugging in a value and see where it roughly lands, because these will give you very different answers.
Also, you can put the function. Let's see if.
Yes.
Yes, you can. Yes, you can. Yes, you're not wrong. And by the way, if we remember this, just as a note, maybe a refresher. So I'll do this for the very simple case of the linear function y is equal to x. If I add 1 to this, then it goes one step up.
Yeah.
I don't know if you remember this. If I do minus 2, it goes 2 steps down. And so already, because I know that here the y-intercept is positive, and here it should be positive, then probably B is not the answer. So that's also another way to obtain the answer. Right now, I'm just giving you ideas and ideas. So that's something. Let's see if we can do one more problem. Yeah. What do you think of this? Just the same ideas. Same ideas we've implemented so far. So the answers all are linear equations. This looks like a, you could just fit a line there and it would look nice. So linear equation, two things, slope and y-intercept. What can you say about them? I'll personally draw something that looks like this. First equation tells you that the y-intercept is going to be 0. So this is definitely not the answer. The other three have a y-intercept of 100. Okay. Doesn't help us much. But then we need to figure out the slope because these are very different slopes. So with one step x, either y changes by 50 steps or changes by 100 or it changes by 200. Now let's see for ourselves. This is 200-ish. And here, roughly, yeah. So this is a change of 100. Here there's a change of 1. So the slope is a change in y divided by change in x. It's 100 over 1. It's 100, roughly, of course. So this is, again, an estimate. Then probably that should be our answer.
I don't understand how this point, this point, in the size of the two, there's a point between 2 and 220.
There's a point between 2.
Like x equals 2 and y is 225.
You mean this one?
Yeah.
Well, here's the thing. This is noise. So this is a noisy y is equal to 100x plus 100. That's really what it is. Because here's the thing. I really like what he said now. Because you have this on down below, but you also kind of have something like this up top. So I don't want to say this, but kind of balances out roughly.
It's more.
Yeah. Well, yeah. It takes more of the points. I would probably say the line that goes right in the middle.
Because it's the average.
Kind of. So in this case, it's a good idea to use a linear function to approximate it. But if we take, let's say, a degree 2 polynomial to approximate this, then I think it will be very bad. If you want to fit this, like this, it's just horrible. So this is actually how people do data analysis. They need to choose the right function. And if they choose the right function for their data, then they can make useful predictions, because this is only useful for predictions. I want to know what's going to happen when you have x is equal to 4, using just these points, these random points, and so on and so forth. So that is at least some insight into the practicality of. Yes.
100 that we got. It's like the result. Slope over the It's only the change of y.
Change in y divided by change in x.
X.
Yes. The change,
Isn't that, it's not the slope, right?
it is.
This is the slope.
So the change in y divided by the change in x is the slope. The slope is precisely the rate of change
Other value,
of
like always there is the slope and other value.
the constant, the y-intercept.
The y-intercept.
The y-intercept. So the y-intercept is roughly here. What I did is, I know this is going to be a linear equation, so I just said, okay, let me draw a line. I just sketched some random line. You could sketch a random line. It doesn't have to be precise. You just need to get a rough estimate, because already the differences are sparse. Between 50, 100, and 200, there is enough space for you to make a nice approximation.
Or for example, like quadratic slope, the y-intercept also is gonna be the constant.
Yes, actually yes, because if you go here, this is a degree 2 polynomial, right? You just plug in x is equal to 0, then this is a times 0 squared plus b times 0 plus c. So this is 0, this is 0, and you just get c.
What's the slope is gonna be in this case?
So the thing is, quadratic functions don't really have a slope, just like linear functions. For this, you need to study something else. So there is this idea where you could use lines to approximate slope, but do you see how on this curve at each point there's a different slope? So take a look at this again. Let me do it again. So here there's the slope, here there's the slope,
That's why like
here there's the slope.
feel like range representation, something like from that to till that, from negative infinity to infinity. That's the slope of negative something.
No. So you need a more advanced treatment of this. It's something called calculus. So here you see that it depends. The slope really at the point depends on what x is. So if x is right in the middle, then it's just a flat line which has a slope of 0. But if you go here, the slope is negative, and if you go here, the slope is positive, which is also the rate of change. So the rate of change is positive because we're going up. Rate of change is negative because we're going down.
The slope from any 2 points in the like quadratic.
You can, but it won't be accurate. So
Yeah, it's not
just use these 2 points, for example, they have a big distance. This is a point on the quadratic, and this is a point on the quadratic. The slope is going to be this.
It's not only it's working for linear function. Maybe.
Yeah, but in this case, it would compute the average behavior of the function, if you're wondering. On average, this is the rate of change. I go from here to there, but I mean, we can see that this is not the best model, at least in this case. So I think this is a good point to conclude. I think this was very nice. We did lots of exercises and we covered lots of good ideas. And we also made mistakes, which is very important. You should not be afraid to make mistakes on your way to success. So thank you very much for joining. It's been an absolute pleasure. And I'll see you next time. And if you have questions, I'll be here. Yeah, of course. And all of the worksheets are on Moodle, so you should do them. You should definitely do them. I think if you do all of the exercises, I think you'll be very well in the exam. And let me know if you have questions. All right.